First of all, thank you for inviting me to, or having me to give this first of these SciStar talks. I was just saying, I think it's a really good idea. We give lots of different types of talks as researchers. So there are outreach level talks, which might be to school children or the public. And we give research talks, which are to our peers. And I remember as an undergraduate attending research talks, and they sort of often go right over your head. But at the same time, the outreach talks are maybe a bit too lower level. And so I think these are an excellent opportunity to sort of get an idea into some of the research that's being done at Queen Mary, and what are the outstanding problems, what kind of things are interesting at the minute that are being looked at. I have come up with quite a broad topic for today. So what it's going to be all about is how stars, the energy they emit, affects their surroundings. So, and that process is called feedback. And so, as we'll see, stars can affect their sort of natal cloud that they're born from, but they can also affect the way that their host galaxy evolves, as well as planet formation too. So it's a really sort of pervasive effect, and we're gonna look at those in turn in a bit of detail. I just wanted to, and I wouldn't normally put this on a talk either, introduce myself a little bit. Again, this is thinking about you as students who may be interested. Some of you in an academic career, even if it's not something that you necessarily want to do, you might be interested in how it works. So I'm a relatively recent addition to Queen Mary. I started at the university in October last year. So I came here with a Royal Society Dorothy Hodgkin Fellowship. So that is, I wrote a proposal saying what I was going to do over about a 5-year timescale in terms of research. And I submitted that along with a whole bunch of other researchers, and it was chosen as one of the ones to get some money. So that funds most of my salary for 5 years, and ring fences time that I can spend doing research. However, the way it often works these days is, in order to try and get a permanent job as a lecturer, you need to use a big chunk of money like a fellowship as a bargaining chip, essentially. So I sort of said to Queen Mary, I've got this big chunk of money, is there any way this job can be made permanent? And so in return for lecturing, doing a half load of teaching, this is now a proleptic position. So that means at the end of my 5 years, unless I do something bad, I should be carrying on. And the course that I started lecturing in the start of this year is the master's level EM radiation and astrophysics course, which I really enjoyed. It's sort of very linked to the research that I do, and I try and make this course as research oriented as possible too. So that's who I am, and I'm going to try not to gesture because I'm doing it on an iPad, because it means that I can do things like draw on it and you can see me at the same time. But if I then gesture wildly, it will flip the slides. So apologies in advance if that happens again. Yeah, so that's who I am at Queen Mary now, but I did my undergraduate degree at the University of Exeter, where I did a 4-year physics with astrophysics MPhys. And then I stuck around and did my PhD there too. I really loved it in Exeter, so didn't want to leave. And then I went to Cambridge at the Institute of Astronomy there for 3 years as a postdoctoral researcher. So once I had my PhD. And as a postdoc, you essentially you're assigned to someone to work with them in a sense. So I was working with somebody called Kathy Clark, but she was very good, and she allowed me to pursue my own ideas as well. And then based on those own ideas that I was exploring, I got a junior fellowship at Imperial College London. And then, yeah, once I finished there, was lucky enough to get this fellowship to bring to Queen Mary. And over this timescale of about a decade, I've published something like 18 first author papers, the ones that I've led, and something like 26, maybe as of yesterday, 27 papers that I've contributed to as well. Right, so I just wanted to do that just to give you an idea of who I am, especially if someone new, so a lot of you probably don't know me. So I said on the first slide, this is all going to be about stars and how they affect the way that galaxies evolve, as well as the way that planets are formed. But first of all, I just want to try and set the scene a little bit. Astrophysics is, it's nice to look at sometimes, but it's hard to conceptually get a hold of. How big is a galaxy compared to a planet, compared to a star and a star-forming region? So we're going to start off with this illustration of how big the extreme deep field is. So what I have here is the moon. And then to scale, there's this little box down here. So this is the size of the Hubble Extreme Deep Field relative to the size of the moon. So Hubble stared at this little patch of sky for a very long time, and what it saw was this. So pretty much every object there is a galaxy comprising hundreds of billions of stars. There are a couple of individual stars in this field, but it's mostly galaxies that you are seeing. I was working out, I think this morning, I can't remember the exact numbers now actually, but you know, if you get a 747 plane and started off on the left-hand side of this image and have it fly at top speed, it takes something like 1 billion times the age of the universe for it to get from one side to the other. So this is a ginormous field here, and it's full of galaxies. But when you compare it to the whole sky, you think about how small the moon is on the sky. Oops. You know, this is just a little box this big. So you translate that across the whole sky, and you get some idea of the scope of the observable universe. This is bigger in scope than we're going to be thinking about today. But let's pick a galaxy, say this one down here. If you were to zoom in on something like this, then this is what you'd see. This is the Whirlpool galaxy. And it has a central nucleus and these spiral arms. And as I said, this is a collection of a few hundred billion stars, as well as gas and little solids like grains of sand called dust. So let's just zoom in. And you can see that in the spiral arms, there are these dark lanes. And those are denser, dusty, gassy regions. Now, if you want to make stars, you need material to make them out of, right? And so this material getting swept up in these arms here is providing you the resources to produce your stars. This is the logical place to produce them. And you'll notice that it's not just dark, there are these brighter red regions. Let's choose one of those and zoom in and see what you might see if you were to look at one of these red regions. I think someone pointed. Somebody's noisy. Hang on, you can mute them if they're... Okay, stop. Yeah, so this is the kind of thing you'd see if you were to zoom in on a star-forming region. One of those bright bits in the spiral arms. So you have a group of stars here that have formed out of that swept up gas and dust in the spiral arm of the galaxy. And then you have this, what looks like a bubble around it. And there's these things like pillars. You might recognize this thing down here as the famous pillars of creation. Okay, so let's keep going. This is, actually we're going to zoom in on the pillars of creation. I expect many of you will have seen this image before. And we're going to be talking a little bit today about why the name, maybe the pillars of creation, is not so good a name for this object. And the final scale to look at on our tour of the things that this talk is going to be looking at is the planet formation and the planet forming disks. So if we zoom in further and look at a young star, you would see something like this. So this is a young star in one of these star forming regions. And you see around them, there are these dark silhouettes. So here is two disks, one here and one here. This one is face on. So the star is in the center of a flattened disk. So you can actually see the star in the middle. And this one is edge on. So the disk is oriented like this. And so it blocks the star's lighting. So in this talk, we're going to be looking at how the star forming region, the stars in the star forming region don't just affect the gas here. We're also going to be looking at how they can affect the galaxy and also affect the planet formation. So the last thing we're going to do before we get stuck in is just think about the range of, quantify a little bit the range of spatial scales that we're going to be thinking about. We've just zoomed in from a galactic field into a galaxy, into a star forming region, into a planet forming disk. Well, let's say that the planet forming disk was as big as an ant. It's a small little dark fuzzy thing in this picture. An ant's not a bad representation. Well, this star forming region on the right here, compared to the size of an ant, a disk, is like comparing the London Eye to an ant. So it's a ginormous scale, and maybe it's not too surprising that something that big can affect something as small as a planet-forming disk. But what about a galaxy? That's pretty big. Should it really be able to notice a star-forming region? Well, the spatial scale, if the planet-forming disk was an ant and the star-forming region was the London Eye, it's still a bit harder to get something conceptual to get the scale of a galaxy here. But if you put a pin on Google Maps at the location of the London Eye and then draw a region that would be, the size of a galaxy compared to a star-forming region, so this size compared to this is about this compared to this. Okay, so you've got a circle that's going beyond Dunkirk, nearly as far as Cardiff and more north than Nottingham. So there's a huge range of spatial scales here. And if you're interested in the planets themselves, they're sort of molecule sized in this picture. Okay, so what we're going to do first is look at how feedback, energy injected by stars, affects star formation. Now, the golden rule of outreach talks, and in fact most research talks, is never stick any equations in. But being physics undergraduates, I thought I'd better stick some stuff in. And this is what you may have come across, or probably will come across during your undergraduate studies when you're looking at star formation, should you ever do so. So what we're interested in here is if you have a cloud of material, what is the maximum amount of material you can have there before it collapses to make a star? Okay. So the processes that are competing are gravity, which tries to squish the cloud, and the thermal pressure, which tries to stop the cloud collapsing. You try and squish a balloon and the air inside pushes back. So you've got that versus gravity. And a simple way of working out when a cloud should collapse is by looking at something called the Jeans length. So here we have a cloud of fixed density rho and a temperature T of a certain size. So as I pile more mass onto this, because I want the density to stay fixed, it just gets bigger and bigger. Okay, so what we're after is a critical size at which your gravity will win and just squish the thing. And what we care about is something called the sound speed. So this is just the Boltzmann constant times temperature on the mean particle mass square rooted. So if you were to give the side of this cloud a flick with your finger, that information, that perturbation would propagate through the cloud at this speed, at the sound speed. So conceptually, what this Jeans length is saying, at what point would the cloud just squish due to gravity quicker than the thermal pressure could even realize it's collapsing? Okay, so can it collapse down to a star faster than the sound speed can propagate through the cloud? That's all it is. So the crossing time scale of the cloud is 2 times its radius divided by the sound speed. Speed equals distance divided by time is all I'm doing here. It's nothing complicated. And I'm not going to tell you where this comes from because we don't have time, but this is the free fall time for a cloud of density rho to just collapse under gravity. So all we do is equate the two. When does this equal this? Rearrange, and you get then a maximum size beyond which your cloud would collapse. So that's the Jeans length. And once you exceed that size, you collapse and make a star. That's probably what you'll learn at some point. So let's look at what happens in a sort of more realistic scenario. Here we have a cloud. It's spherical, like the thing we were just looking at. But nothing is ever spherical and completely static. This is a cloud that is gravitationally unstable, but it's also turbulent. So as the simulation evolves, and this is from Matthew Bate at the University of Exeter, you'll see that it doesn't just go and make a star. It produces these things we call filaments. So they're sort of long, thin bands of the yellow stuff. They're dense filaments of material. And those filaments channel material down themselves. And where you get these filaments intersect, we call those hubs or junctions. And that's where you concentrate all your material and start producing stars, which you can probably see as these little white dots that are popping out. Okay, so you've got filament here, and there's your stars being produced. So this simulation describes to a computer, basically, how fluids move around, and also how gravity works, and has a recipe as well for sticking in stars when it thinks they should be formed. and it's a beautiful simulation. But it doesn't actually really look all that much like the image we looked at earlier, right? This star-forming region's called the Eagle Nebula, this thing down here. And this is the simulation. So, what's missing there? What's different? I should point out this simulation does do a heck of a lot of stuff very well. But something's missing to make the star-forming region look like this. And the answer is going to be something called photoionization. And again, this is something I would just sort of say in a research talk and skip over in a outreach talk. So this is stuff that's in there because you guys are physics undergrads. So I have here on the right a pretty poor schematic of a hydrogen atom, just learn in school, a proton with an electron going around it. And from your quantum mechanics courses, you will know or will know that the energy states this electron can have are quantized. So it can have some lowest energy state, and then there's a ladder of other possible energy states it can have. And if a photon comes in and gets absorbed by the atom, that can excite the electron up to some higher energy state. And if the atom then wants to decay back down, it has to emit a photon again to conserve energy. Well, what happens if the photon that comes in is of sufficiently high energy that you can launch the electron to n equals infinity? Well, then you ionize the atom. You end up being left with an isolated proton, and the electron just shoots off. And the wavelength you need to do this for hydrogen is 91.2 nanometers. So the wavelength has to be less than that, which corresponds to an energy of more than 13.6 electron volts for your photon that's coming in. If the photon has higher energy than that, you can ionize hydrogen. And that process is called photoionization. So it's quite simple, but it has a big, complicated name. So where do those ionizing photons come from? I should quickly say, one thing I've missed there actually is that that energy from the photon that gets absorbed and ionizes the hydrogen, that energy now goes into kinetic energy. Okay, you had a hydrogen, and now you've got an electron that's zipping around with all this energy. So the gas has more kinetic energy when you ionize it this way, and that therefore means it's hotter. So an ionized hydrogen gas is about 10,000 Kelvin. So what makes these ionizing photons? Where do they come from? Well, in astronomy, we classify stars using there's a spectral classification scheme. So the sun sits around here. Low mass stars are M stars on solar radius. If I take a 40 solar mass star, it's more like 40,000 Kelvin in temperature, and it's about 8 times bigger, say, than the sun. So another equation, this is just the luminosity of a spherical black body. Again, I expect many of you will have come across this. If not, you will soon. This might even be a sort of school thing. So this is just the luminosity of a black body is 4 pi r squared. So this is a spherical surface, times a constant, times the temperature to the power of 4. So let's see how much more luminous our 40 solar mass star will be than a 1 solar mass star. Let's just plug in what we know the radius and temperature are. Well, if you do that, so just how luminous a 40 solar mass star is divided by how luminous a 1 solar mass star is, you find out that it's about 10 million times more luminous than the sun. Okay? So hang on. So yeah, 1 40 solar mass star is 10 million times more luminous than the sun. So even if you had 40 suns, they're still nowhere near as luminous as 1 40 solar mass sun. Okay? Just because of this, there's this temperature to the 4 thing here. So 1 40,000 Kelvin star is way more luminous than 46,000 Kelvin stars. And the luminosity is only just part of the picture. Yes, the massive stars emit way more light in total, but it turns out that the light they actually emit is way more energetic too. So the spectrum of a black body, which is how much of the light is emitted at different wavelengths, is given by this thing called the Planck function. It's a horrible looking equation, so let's just look at it. So this is, the axes here are how much light is being emitted, and the x-axis is at a particular wavelength. The blue line here is for the sun. So the sun peaks at around about the visible part of the spectrum, which is what you'd expect, and then drops off dramatically as you go to sort of stronger ultraviolet wavelengths. This black line here is the wavelength to the left of which your photon would be able to ionize hydrogen. So this is what we're interested in for being able to ionize the gas. So yeah, this was the sun, this blue one. This orange one is the sun times 40. So you see it makes almost no difference and gives you almost no more photons out here where we care. And this thing up here, this beast, is 140 solar mass star. So its peak, it's not just brighter, but its peak has shifted to the left. So it emits way more high energy photons. You need some pretty strong sunblock near this thing. So let's count up the number of photons you get to the left of this black line, how many ionizing photons you get. Well, the sun emits about 10 to the 34 of them every second. 40 suns, let's just times that number by 40, gives you about 4 times 10 to the 35 ionizing photons per second. What about our 140 solar mass star? That gives you about 4 times 10 to the 49 ionizing photons per second. So what does that mean? Our single O star emits 100 trillion times more ionizing photons than 40 suns. There's our little interlude that I would not normally give in an outreach talk. So let's go back to the simulations. Okay, on the left, we're going to have pretty much exactly what we looked at before. It's a spherical turbulent cloud that's going to collapse and produce some stars. The code knows about fluid mechanics and gravity. On the right, when you make a massive star, the effect of this ionization on the gas is going to be accounted for. So the hydrogens will have their electrons stripped off, and that will heat the gas up to about 10,000 Kelvin. So they've got identical initial conditions, and then you start to produce your stars. And on the left, the gas stays relatively, where the stars are. But on the right, because of the photoionization, the energy from the massive stars, the gas is heated up to about 10,000 Kelvin. It's very overpressured compared to the 10 Kelvin surroundings, and you get this bubble that expands. This is why we spent 5 minutes talking about what photoionization is. It has a dramatic effect on the morphology of the star-forming region. And one cool thing is that these filaments we were talking about earlier that channel the gas down to the stars, well, they're pretty dense. So they actually are less destroyed less quickly by the evaporation. And so that's what ends up giving you these pillars. They are the denser stuff. I should say as well, I'm not sure if I'm seeing questions come in. If maybe someone could take charge with flagging me down if they are coming in, and we can stop and discuss stuff.
Yeah. So the person asked, what software programming language did you use for the simulations?
So I didn't run any of these ones. So the first one was by Matthew Bates, and these ones are by a guy called Jim Dale. And they were both written in Fortran. So this is an older code you probably won't come across in your undergrad studies. But it's fast, which is why it's used, as is sort of C. So on a supercomputer where you run these kind of things, you don't really want to use Python. But for the majority of applications nowadays, people do use things like Python for their coding.
Thank you.
If there's any others, yeah, feel free to, maybe if you could take charge with flagging me down to answer them. So yeah, now we come to one of my favorite things, I think, in my career. Over the 10 years or so, I remember the day doing my PhD where I looked at this region and thought, wow, I actually sort of know what happened here now. It's one of the most beautiful images, I think, in astronomy. And you can now look at this and conceptually understand roughly what happened. There was some cloud. It wouldn't have been spherical. That's just what the models have to start with something. But it was gravitationally unstable and turbulent and collapsing under gravity. You'd have had filaments forming, probably here, here, and here, and they would channel the material down to the young stellar cluster, which is here. And then one or more massive stars, these O stars, were formed, and they emit this high energy light that starts to heat up the surrounding gas to 10,000 Kelvin, which gives you this hot bubble that expands. So this stuff in here, this blue stuff, is 10,000 degrees, and this stuff out here is about 10 Kelvin. And you know, these were filaments, but now they're in the process of being destroyed. So this is why I'm saying that, you know, calling them the pillars of creation isn't necessarily that accurate, because they were once upon a time creating, but now they're more, you know, the star formation is being shut off at this point. So we've talked a bit about photoionization feedback. There are other types of feedback too, like winds that can be launched from the stars, but we won't talk about those today, just in the interest of time. But another obvious thing is supernovae. These O stars, they only live about 5 million years, which is very short time in astrophysics, and then they explode catastrophically. So this is a very recent paper, only from this year, where they're looking at the effect of supernovae on these star-forming clouds. And interestingly, what's very interesting from my point of view is how the different types of feedback influence one another. If you just take a cloud like this that you can see and set off a supernova, kaboom, it has a pretty dramatic effect on the gas, right? It's in a very short space of time, blown this great big bubble that's injected loads of momentum into the cloud, pushing all this material away. But the O stars, before they explode, they're emitting all these high energy radiation. They emit winds, which already does a good job of blowing a bubble in the gas. So this is the same kind of calculation, but they've already allowed, before the supernova goes off, that ionizing, that photoionization to happen, to blow a bubble. And what that has done is sculpted channels through the cloud that are very low density. And so what that means is when you let your supernova go off, which I'm going to do now, boom, that energy all just escapes out of those holes. And the cloud barely notices the fact that a supernova went off. And that energy, therefore, is just going to escape into the wider galaxy, which leads us into part 2 of the talk, which is how are these star-forming regions? We've talked about how it can affect the star-forming gas, and I should quickly say before I move on that research to do with that has been asking things like, what does that feedback do to the star formation in that region? Does it make stars where you otherwise wouldn't have had them, or does it completely shut off the star formation? Various things like that are questions that have been asked in recent years. But the focus now is turning towards what happens at bigger scales. What happens to the energy that gets out of these star-forming regions? How does it affect the galaxy? So here I have a image of the VLT, the Very Large Telescope, with its laser guide star pointed at the Milky Way. So this is our galaxy. We are sitting in this flattened disk of stars and gas and dust. So it looks like a band across the sky. And we're going to look at another simulation now, where their approach is that they still want to be able to model the star formation, like we were just looking at in those simulations, but they also want to look at bigger scales too. So what they do is they've essentially drawn a box on the galaxy like this, and they're saying we're going to model a region like that and see what the feedback does to the galaxy. So this is another simulation led by Steffi Walk's group in, is it Heidelberg? No, it's not, Cologne. That's where they're based. So you're going to see there's a lot of information here, but there's a bunch of panels. This is the one you want to look at. So this is like looking at the Milky Way in the sky. And it's just going to be allowed a little bit of time to just evolve and settle down before they start doing anything to it. So it's not making any stars yet. It's just a Milky Way in the sky, just the gas just settling down. And in a minute, you'll see little dots start to appear. Like there's one, and they're going to start exploding as supernovae. And so this here is the temperature. You can see it's getting way hotter. And this is various compositions of hydrogen. So this stuff is ionized hydrogen, atomic hydrogen, so just protons with electrons. And then this is our molecular hydrogen. So that's where those different species are abundant. And you can see that when the supernova go off, they blow material to very big heights above the galactic disk. So here is another simulation, only this time they're, again, combining the effects of the radiation with the supernovae. So they're not just allowing the supernova to go off and blow away all the gas. You know, the radiation makes those holes, and so the supernova energy can just escape more easily. You know, evolves in the same way for a little while before the stars form. boom, the supernovae start going off as well. And again, you've got material being blown to larger heights in the disk. Now, probably to many of you, you're sitting here thinking these just look the same. They're messy, colourful, whatever, maybe interesting to look at, but I can't really tell any difference. So this was the supernovae only. This is the density. That's the middle of the galaxy, and this is moving above it. And then this is when you have the radiation as well. So just qualitatively, I'm flicking back and forth between them. You can see there's a substantial difference in that when you have the radiation feedback as well, the galaxy ends up less puffed up. Okay, whereas with supernovae only, material gets blown right out of the galaxy. And we're not, oops, sorry, it's the third time I've done it now. We've talked about qualitative stuff so far, but what about some numbers? What is actually, is there anything really meaningful that's different between these simulations, or do they just look a bit different? So what we're plotting here is the rate at which stars are produced. So how many stars, or how much mass in stars is produced per year by your galaxy. And the blue line here is if you have the supernovae just blowing up, and then the ones down here if you have something like winds or radiation going, like doing something before the supernovae. So the mass in stars per year varies by about an order of magnitude here. So if you want to understand, what the galaxy looks like, where the stars came from and when, then you need to be getting the feedback right. It's having a quantitative difference. This is another set of simulations of galaxy evolving. Again, it's all three panels are going to be identical starting conditions. The top ones will be looking down on the galaxy, so it should look like a spirally galaxy. And at the bottom, it's like looking at the Milky Way in the sky. And what's happening from left to right is the amount of energy from feedback is increasing. So here it's relatively weak, and you get a fairly large extended galaxy. You can see the little puffs going off where the supernova and whatever the feedback is they're doing is having its impact. And then these ones, you can see they're much shorter, they go much smaller, they go through these transient events where they almost get blown apart, and they're much more puffed up as well. That's what you're seeing on the bottom. So the galaxy definitely notices what's going on these smaller scales. But now we're getting into, I said I wanted to highlight ongoing research and unsolved problems. Well, if you want to model an entire galaxy, or maybe you've seen these simulations where they model a big chunk of the universe, how on earth can you get right down to those small scales and properly model what's going on with the star formation? And we're going to talk a little bit here about subgrid physics, where you basically say, well, I can't model it, it's too small a process, so I'm going to sort of fudge it a little bit. So what is the problem? Let's revisit it. Let's say I want to model this galaxy here. When you are modeling something with a computer, if I want to model the air in this room, I cannot possibly track every individual molecule in the room. My computer is just not powerful enough. So what I would do is break it into blocks, maybe cubic blocks, and just say, there's this much density in air in the room. And if I turn a fan on over there, air is going to be blowing this way. So I just, in my box, work out the amount of air going out this side and the amount of air going in this side. And that will tell me how the wind is blowing around the room. So you have to break up space into little blocks. This is called discretization. And your block can only get so small before your computer just grinds to a halt because it doesn't have enough memory. And so here on the right are a bunch of structures, maybe spiral galaxies. And on the very right is a sort of a grid that you might use to try and model them. We use a clever approach called adaptive mesh refinement. So that's saying that, in this case here, I don't really care what's going on out here. There's nothing interesting. So let's use big blocks. Okay, it saves some memory. But here is the interesting stuff. So let's use very fine blocks. But it turns out if you're trying to model a whole galaxy, computers just cannot get down to that small scale where the simulations of the spheres collapsing, you just can't do that. It's not enough memory, not enough computational power. So I've just stuck someone else's slide on my slide here. This has given rise to something called subgrid physics. Okay? In subgrid physics, you say, I'm modeling a galaxy. I can't possibly directly model the feedback. So I'm just going to, am I going to say arbitrarily? Almost arbitrarily say, I think some star formation happened there in my galaxy. It's dense enough. It's all converging together. Let's just stick in a bunch of energy to represent a supernova. And how much energy and momentum we pump in? Well, let's just tune it so that when our simulation's finished, we get the right answer. And that's essentially what's done with this subgrid physics. The reason I've used someone else's slide here is so that I can not be accused of sort of standing here slating a field I'm not really part of. This is a talk from someone else who's an expert in the field. And they say in this third bullet point, you know, all galaxy formation simulations rely on subgrid physics, you know, numerical modules that are nearly arbitrarily calibrated to fit predetermined outcomes. So that means, you know, you've got a calculation, you're trying to model a galaxy, and if the way you prescribe your feedback isn't right, well, you just tune it until it looks right. So the question is, what do you learn? And you know, it's not necessarily clear what you do. So that to me is one of the big problems in large-scale astrophysics modeling at the minute. You know, the feedback is very important, it affects your results, but it's not necessarily that self-consistent. But something that's really changed in recent years is the large-scale people are talking to the smaller-scale people like me, and we're trying to figure out, you know, things like that result from Lucas et al. We saw, where if the supernova goes up in the cloud, it has a very different impact if the radiation's already blown a hole for that energy to escape out of. So those conversations are happening to try and improve this. Anyway, back to the slides. This is just again illustrating the impact of this subgrid physics. So this is from the EAGLE calculations, EAGLE simulations, and they're simulated observations of the stars in the galaxy, of the starlight in the galaxy. These are not real galaxies. And this one I think is one which they term as their most right one. And then this is changing that subgrid physics a bit, and not dramatically enough that you get a completely different looking galaxy. You know, it's still roughly the same size, but there's different types of stars. So you've got a lot more bluer stars here, and the distribution is different of material. You don't really get any spiral arms in this case. And then, you know, these ones are way more puffed up, for example. So it has a real impact, the way you just tune this number to get the right answer. And this is just another example of the same kind of thing. So this is from a huge simulation called Illustris. And again, here you have, this is gas density, the green, and you're looking down on a galaxy here. And this is where the stars are. This is if you have no feedback. So you can see that's pretty nuts. There's no galaxies that look like this. And then these are different ways of implementing that subgrid physics, and you know, your answer changes. So we're nearly there. I haven't got very much time to talk about the bit I actually know most about, which maybe is a good thing. So we've talked about star forming regions, how they inject energy, they can blow the material away, and that energy can get into the wider galaxy. But these young stars are also trying to produce planets. And so the question is, that same energy that can destroy the star forming gas and blow it away, what can that do to the planet forming disks? And I've got here just an artist's illustration of a star with its young planet forming disk of material around it and a stellar neighbor shining on it and stripping material off in a wind. So what's going on here? Just in the final 5 or 10 minutes. So I'm sure many of you will have heard in the news lots of stories about exoplanets. As of last year, we've now discovered more than 4,000 of these things. So planets orbiting stars other than the sun. And what's pretty amazing is that these planets are just really broad in their characteristics. They're really diverse. And to give an illustration of that diversity, what I'm showing here on the y-axis is the planet's mass, and on the x-axis is its orbital period. So that's the length of its year. And closer in planets go around more quickly, and further ones go around more slowly. So this is basically the distance from the star. This is Pluto's orbit. We've got some solar system planets. So this is Mercury, the Earth, and Jupiter. And the black points are all discovered exoplanets. So you have things like lava worlds and hot Jupiters close in. And you've got the rocky planets, ocean worlds, and cold Jupiters. We've found things further out than Pluto, and the vast majority are actually closer in than Mercury. So these are unlike anything in our own solar system. This diagonal line here represents our observational constraints. So we either haven't been looking for long enough, or our telescopes just aren't good enough to find planets beneath this line. So wherever we could have found them, we pretty much have. There's a couple of exceptions, like what's going on up here. But I'll come back to that in a second. So we've got all these exoplanets, and what we really want to do, one of the biggest problems in astrophysics now, is understanding why planets in the universe are so diverse. Okay, and in doing that, we maybe understand how common solar systems like our own are, which is of course a very important question as a species. But in order to achieve that, we need to understand how the planets are born, and also we need to understand how they subsequently evolve. So I personally think the main thing is how they're born, what gives the initial condition, the initial planetary properties that result from those disks. But the subsequent evolution is important, because that's what's thought to be going on here. These are planets that are very close to their parent star. It turns out if you put a planet in here, its atmosphere will get evaporated so quickly by the star that it will shoot down here and lose it. So there's processes like that, but other than that, I think we need to understand how planets are born to understand the diversity of planets. And we can skip through this quickly because we've already looked at this image, but planets are born from these flattened disks of material that are spinning around young stars. So again, here is a face on one, you can see the star, and here is an edge on one, you can't see the star because the disk is blocking it out. Our view has changed a lot since the mid-90s, so that's when those last two images were taken, 96. In 2015, ALMA, the Atacama Large Millimeter Array in the Chilean desert, looked at a disk called H-Hel Tau and blew everyone's minds because we saw these concentric rings in a disk. So this is an observation of like small solids, little grains of sand, if you like. And of course, everyone wants to jump on this and say, it's planets, it's planets. We've seen planets sculpting features in a disk. It turns out there's quite a lot of things that actually could be doing it, and planets is just one of them. Then this is TW Hydra has had these rings found. And then only a couple of years ago, there was the ALMA D-Sharp survey. So the point here was to go and look at a whole bunch of disks that weren't necessarily that interesting from what we'd seen before, and just see what you can see. And all of them have substructure, be it spirals or rings or whatever. So the picture we might have had from the late 90s, if you go back and look at these, of a smooth continuous disk is dead now. And a lot of work is being done. The majority of the planet formation community is working with these kind of images, trying to understand how they fit in with planet formation. But, I'm getting ahead of myself, these disks that you can see on the screen are all relatively close by to the sun. And that is because they're brighter, and you can also resolve structures like rings in them more easily. Okay, if I was to hold my fingers up and walk backwards, you've only got a certain number of pixels on your screen. Eventually you won't be able to distinguish my fingers are apart. So as these disks get further and further away, it's harder to see these rings. Now, it turns out that near the sun, there's not really any of these O stars. There's no massive stars. So the radiation environment is actually very gentle. So these things, it turns out, are rare. They're not common. They're not what most planet-forming disks would be like, because they're in this very gentle radiation environment. And we do know that if you stick a planet-forming disk near an O star, it has a massive effect. So this is an image of Orion. And in these little boxes, got zoomed in here, what the planet-forming disks look like. And you can see that they don't look very disky anymore. Let's just go on to a better gallery of them. They look more cometary. And that's because the disks are being shone upon, they're being heated and ionized, and they're losing huge plumes of material that are being driven away from the disk. And this dramatically shrinks the disks, which affects where you can make planets, which might be important for planet diversity and explaining that. And it reduces the amount of mass in your disk. So again, that potentially limits the planets you can make and could help explain planet diversity to some extent. And it also affects your lifetime of your disk. We can work out how much material the disk is losing, and it can't sustain that for very long. It's just going to disappear much more quickly than those nearby disks that we're spending so much time looking at generally as a community. So the radiation from stars certainly can affect planet formation. But how important is it? I said that these things over here that we're spending a lot of time looking at are rare. Well, it turns out that planet-forming disks sitting next to massive stars are also rare. Okay? They're both extremes, extremely strong UV field and extremely weak. So my research and what I'm world leading at the minute for is trying to understand how, what is going on for the most common environments that young stars find themselves. What happens to most planet-forming disks?
Hello there.
Yep.
We've got another question.
Okay.
Are these concentric rings the Lindblad resonance bands? And what, if any, situations does photoionization play a role with Lindblad resonance bands?
That's a very good question. I think I'm going to be sly with the first answer, which is to say that I think it's still not conclusively determined what is causing these rings. There are lots of different possibilities. So I'm not going to say that they are Lindblad resonance bands, but yeah, there's lots of possibilities there. In terms of how photoionization interplays with that, I don't think that's been looked at. My expectation is that it's not very important at all, probably, because you have two sources of ionization, one from the host star and one from the surroundings. And the host stars gets blocked off pretty close to the inner part of the disk. Whereas this image here, I forget how big it is, but it's much, much bigger than the effect of radiation from the parent star. But that's a good question. Go ask Simon Ann or Richard Nelson or somebody else. You're probably working with them on a project given that question, so they could probably give a much better answer than me. Okay, so we want to know what's going on in the middle. What do most stars experience? And so what I'm doing in my research at the minute is running currently the only calculations globally of disks being shone upon and evaporated in these intermediate ultraviolet strength regimes. So why am I not about to show you a lovely movie like we've seen for the star formation? Well, there, the photoionization is what makes the gas hot. Okay, so you just got hydrogen, you work out where it gets its electrons stripped off, 10,000 Kelvin, easy. In the middle, where the UV field's a bit weaker, you start to care about something else called photodissociation. So now, rather than atoms being ionized, you have molecules that start to be broken apart. And this is way harder because you have chemistry going on. There's loads of different ways that the gas can try and cool itself down, which are much more complicated than when you're thinking about just stars ionizing the surroundings. So what makes these calculations really challenging is what we call the microphysics. So we're having to do chemistry and radiation and fluids moving around all together. But in the last couple of years, I'm now able to model this process of the disks being evaporated in multiple dimensions for the first time. We could only ever do it in a sort of semi-analytic 1D way before. And the expectation, going back, of what happens in the middle from these kind of models is that actually the effective environment is important still. So most stars, it seems, the planets they end up with is sensitive to where the star itself is born and what its stellar neighbors are like. And at the minute I'm just going to make you take my word for it in a sense, but there are now observational surveys looking at the statistics of the properties of these disks around young stars, which is now backing up this sort of idea. But there's still a lot more work to do. So I'm a theorist who is trying to understand how disks are being evaporated mostly at the minute, but I also work with observations too. And I understand that this is a horrendous looking slide. The problem we have, well, let me just go back. The problem we have is over here, people don't think about the environment. And over here, it's rare and very strong and unsubtle. But in the middle, we've never known what to look for. What does an evaporating disk look like that's only gently evaporating? So with these models that I've been producing, you can also predict what an observer should see with something like ALMA. And that's what this slide is. So this is a prediction of what an evaporating disk should look like if you look at emission from carbon monoxide molecules or emission from atomic carbon, so little carbon atoms with, so they're going to mostly come where your molecules start getting broken up. A moment zero map is basically telling you where the light is coming from. And we will, in my EM radiation and astrophysics course, all of this would be explained in a lot more detail, this kind of thing. But in a moment one map, it tells you the velocity of the material. So this is where the emission is, how it's moving. So for a rotating disk, the characteristic signature is a blue shifted side and a red shifted side because it's spinning. So some is coming towards you. If you think of the Doppler effect, it's blue shifted, and then the other side is red shifted. So that's what you're seeing here. And you get a subtle difference when you look in this atomic carbon tracer. It's like slightly bent, but it's not really unsubtle. But there's something called a position velocity diagram, which is where you basically cut across the disk. And as you do so, look at the speed that the gas is moving as you do that cut. And here, they look drastically different. Okay. A disk just spinning, according to Kepler's laws, all its emissions should be in these white regions. But when you have this, when you look at atomic carbon, which traces the wind coming off the disk, you see this stuff that's going way too fast, and also from these sort of forbidden quadrants. So this is a paper that I published just this year. And so the prediction is that if you were looking in carbon monoxide, which is what everyone does because it's easy to look at, you're never going to see these winds. You need to look in this look at atomic carbon emission, and then there's these unsubtle signatures that we've now predicted. And so I'm now writing and have written proposals to turn telescopes like ALMA towards disks in sort of common UV environments to try and find evaporation in action there for the first time. So hopefully that will come soon. Right, to summarize, there's been a heck of a lot of information. I wouldn't be surprised if it's a bit overwhelming. But takeaway message number one, if you don't remember anything else, stellar feedback, that's just referring to the energy injected by stars and what it does to the surroundings. And we've seen how that can affect a star forming region by the gases trying to fall in and make stars, but the feedback blows it away. And we've seen how that feedback can then leak into the wider galaxy, which can affect how your galaxy makes stars. It can affect how puffed up your galaxy is. It can affect all sorts of stuff on a galaxy scale and beyond. And it's also important for understanding how planet-forming disks evolve. They can live for less time. They can be smaller and less massive, and that can all go into affecting the planets that you end up with. So I'll stop there, and if anyone has any other questions, please feel free to ask.
Hey there, I was just wondering if you could go into more detail about some of the options that have been put forward for how rings in planetary disks are forming.
Okay, crikey, well, there's lots. I'd say probably the most popular one is planets. And I don't work on this very much, but people here do, like Sam Parda-Cooper and Richard Nelson. Looking at how planets migrate through disks and the effect that has on the dust, and how you can shepherd the dust into these rings. Some people, there's questions about the numbers of planets. You need to produce different types of rings. Essentially, most disks with rings now have a bespoke model where someone tries to put planets in and demonstrate that planets are responsible. Other things, so one that has now fallen out of favor a bit is the idea of, there's this idea of snow lines. So as you move out, I forget what slides I have as future things. Do I have anything blank? Not hugely. Yeah. I'll just draw one here. Let's say I have a star and a disk. Trying to color it in so you can't see. Now, the star's going to be warming up the disk. So as you go outwards radially through the disk, it's going to get colder, right? So T1 is bigger than T2, and it's smoothly transitioning. It goes about as R to the minus a half the temperature in the disk. And there's various different species in the gas, so things like carbon monoxide, things like molecular hydrogen. And what can happen is they can, if the disk gets cold enough, get stuck on the dust. So the dust is little solids. So you can essentially remove all of a certain molecule from the gas and stick it to the dust. So let's say the temperature at which that happens is here. So in here you maybe have CO, and then out here you have none. Or there's water can do this as well. It turns out that has a little influence on the temperature here and gives you a little pressure bump. That's a terrible schematic. And this can stop any dust that is moving through the disk. It can run into this pressure bump and get stalled there. Okay, so it's a big pile up of dust basically at this location. And that's quite common to lots of the different mechanisms, but the snowline one is one example. So you have a change in the chemistry of the disk, which gives you a little temperature jump, a little pressure bump, and then the dust falling in just gets stalled there and sort of piled up. And that could maybe give you planet formation as well. It's a huge and complex field trying to understand these rings.
Right. Thank you very much.